Hello and welcome to this session on isomerism. I am Maria and I am an attainment tutor in our Faculty of Life Sciences. Step Up to ChemHE is a faculty-wide initiative to assist students in developing key chemistry knowledge that can be applied throughout your life sciences degree. So if you have not done A-levels in chemistry or you feel like your chemistry knowledge might not be sufficient, those videos are designed to help you with some common topics in chemistry. Today, we will look into isomerism. So molecules with the same chemical formula but different structure and characteristics are isomers. The tetravalency of carbon predicts the existence of mirror image isomers, the so-called stereoisomers. Organisms in general impose a chiral environment. For example, we only use amino acids in their L form or sugars in their D form. Enzymes will usually only recognize one type of isomer. The introduction of a wrong isomer into the body can have serious consequences. So let's look closer into this topic. First, let's see what isomerism is. It's the existence of molecules that have the same numbers of the same kinds of atoms and hence the same formula, but differ in chemical and physical properties. In other words, isomers are chemical compounds that have the same parts but are nonetheless not the same. For example, consider two bracelets, each consisting of 5 red and 5 green beads. These could be arranged in many different isomeric forms, depending on the order of colors. Each bracelet would have the same parts, that is the 5 red and 5 green beads, but each variation would be different. Isomers can take many different forms, but there are two main forms of isomerism, structural isomerism and stereoisomerism. We will consider structural isomers first, which can be split again into three main subgroups, chain isomers, position isomers, and functional group isomers. And then we will look into stereoisomers, which could be geometric or optical. Right, so structural isomers, or also called constitutional isomers, are molecules which have the same molecular formula but differ in connectivity. In other words, the same number of the same types of atoms but connected differently. So to start with, chain isomers have the same formula but different rearrangements of the carbon skeleton. Organic molecules are based on chains of carbon atoms, and for many molecules, this chain can be arranged differently, either as a one continuous chain or as a chain with multiple side groups of carbons branching off. Let's look at the molecular structures of butane and isobutane. These are both C4H10, but they're connected differently. The first one is a straight chain of carbon atoms, and the second one has one moved over to the middle. These two butanes have the same elemental composition, but are not the same compound. They're structural isomers. Position isomers are based on the movement of a functional group in the molecule. A functional group in organic chemistry is the part of a molecule that gives its reactivity. Nothing else about the molecule changes, simply where the functional group is in the molecule, and the name simply alters slightly to indicate where the functional group is located in the molecule. So let's look at an example here with butene with the molecular formula C4H8, which is a chain of carbon atoms and has a double bond, but this double bond could be either in the middle or at the end, as shown on the slide. These two molecules are position isomers, and the position of the double bond in their structure is also reflected in their chemical names. Functional isomers, also referred to as functional group isomers. These are isomers where the molecular formula remains the same, but the type of functional group in the molecule is changed. This is possible by rearranging the atoms within the molecule so that they're bonded together in different ways. As an example, a standard straight chain alkene can have an isomer that is a cycloalkane, where the carbons are bonded together in such a way that they form a ring. Different functional group isomers are possible for different functional groups. Now moving on to stereoisomerism. Stereoisomers are molecules which have the same molecular formula and the same connectivity, but they differ in the way they're oriented in three-dimensional space. So in terms of stereoisomerism, there are two main types, as we said in the previous slide, geometric isomerism and optical isomerism. These, as the name suggests, are not to do with any large-scale rearrangements of the structure of the molecules. Instead, they involve different arrangements of parts of the molecule in space. They are a little bit more complicated to think about than the structural isomers. So let's have a look at each of them in turn. So geometric isomerism is actually a term that is strongly discouraged by UPAC, who prefer cis-trans or EZ in the specific case of alkenes. However, geometric isomerism is still consistently used in many A-level courses to refer to both. So for this reason, I've used this name here. This type of isomerism most frequently involves carbon-carbon double bonds, shown by two lines joining each carbon instead of one. And rotation of these bonds is restricted compared to single bonds, which can rotate freely. This means that if there are two different atoms or groups of atoms attached to each carbon of the carbon-carbon double bond, they can be arranged in different ways to give different molecules. These atoms or groups can be given priorities, with atoms with high atomic numbers given higher priorities. If the highest priority groups for each carbon are on the same side of the molecule, that molecule is denoted as the cis or the Z isomer. If they're on opposite sides, it's denoted as the trans or E isomer. The two different nomenclatures are a little confusing. So cis-trans is now less commonly used, with EZ instead being favored. Right, in terms of optical isomers, these are named this way because of their effect on plane polarized light, and they come in pairs. They usually contain a chiral center. This is a carbon atom with 4 different atoms or group of atoms attached to it. These atoms or groups can be arranged differently around the central carbon in such a way that the molecule cannot be rotated to make the two arrangements align. Since one arrangement cannot line up to look exactly like the other, we refer to them as non-superimposable mirror images. So one of the isomers is the mirror image of the other. It will probably help you if you think of this concept as with your hands. So look at your hands. These are mirror images of each other, but you cannot exactly superimpose one hand on top of the other because your thumbs will stick out in opposite directions. Okay, so let's look at why is chirality important. Life forms can distinguish isomers based on their different shapes. Normally, one isomer is biologically active and others are inactive. Our cells have imposed a chiral environment, or in other words, only certain isomers are recognized and incorporated. Problems can arise when an inappropriate isomer is introduced into this environment. So let's look at an example of this. In the 1960s, many pregnant women who had taken thalidomide gave birth to deformed babies. One of the enantiomers, isomer type 1, acted as a sedative, as it was intended, but the other isomer, type 2, caused birth defects. This figure here on the left of the slide shows the two isomers of thalidomide, which differ in the rotation of the ring group about the carbon marked with the star, so the group shown with the purple shading. And the picture on the right shows an example of these birth defects that thalidomide caused. I'm sorry about this picture. It's not a very pleasant thing to look at, but it shows the importance of knowing chirality and isomerism and how these can alter the biological effect of a drug dramatically. Chirality is something that we would typically assign to a carbon that has 4 different substituents, as we've already said, or in other words, we say that the molecule has a chiral center. In the case of chiral molecules, we need to be able to decide if the stereo center is R or S, and this is called assignment of absolute stereochemistry, meaning defining the arrangement of atoms around the chiral center. To do this, we need to follow several steps, as shown on this slide. So the first thing we need to do is find the chiral center and decide on the priority of each atom attached to the chiral center. This is done according to atomic number. For example, oxygen with an atomic number of 8 goes before carbon, which has an atomic number of 6, but carbon goes before hydrogen, which has an atomic number of 1. Then when we've done this, we need to view the molecule with the lowest priority, so the 4th group, which is usually hydrogen, if one of the substituents is hydrogen, directed away from you, so with a dashed line. Then we need to observe the order of priority and join all the groups together. If the direction is going clockwise, the stereocenter is R, and if the direction is going anti-clockwise, the stereocenter is S. Then I have also listed some additional rules here, which I think will help you when you're doing the assignment. So if the lowest priority atom is not on the dashed line pointing away, in this case, the molecule must be rotated. But this is not a very easy thing to do if you're not used to imagining molecules in 3D. So you can proceed with the assignment, and if it is R, then it changes to S and vice versa. If 2 or more atoms attached to a chiral center are the same, then you need to look at to second and third atoms until it is possible to distinguish between groups, and the highest priority different atom takes precedence. And then for multiple bonds, double or triple bonded to an atom means that the atom is connected to the same atom twice or 3 times. So let's try and assign the absolute stereochemistry of the chiral center in glyceraldehyde. So here is the structure of glyceraldehyde, which has 1 chiral center, shown as highlighted in purple. This is a carbon atom which has 4 different substituents attached to it. Now we need to look closer into what these substituents are and decide on their priority. So the carbon is attached to 1 oxygen, 1 carbon, another carbon, and a hydrogen. So the first thing we can do is give the oxygen the highest priority, as its atomic number is 8, and hydrogen the lowest priority, as its atomic number is 1. Then we have 2 carbons to decide from, and to do this we need to follow the structure on each side and see what these carbons are attached to. For this carbon over here, we have a double bond to an oxygen and a hydrogen, and for the other carbon here, we have a single bond and an oxygen and 2 hydrogens, which are not shown here, but you should be familiar with this way of drawing organic molecules after watching the video on organic chemistry visual language. As we said on the previous slide with the steps and rules, when we have a double bond, we consider that the carbon atom is attached to an oxygen twice. So this substituent here will gain priority over the other one, where the carbon is attached to an oxygen with a single bond. This makes this substituent here priority number 2, and then we get priority number 3 for this carbon. Altogether represented in terms of priority, we get this, And now we need to follow the numbers and see if the direction is clockwise or anti-clockwise. In our case here, it's going clockwise, so the stereocenter is designated as R. Here I have some practice questions for you, and the first one is to look at a few drug molecules and identify if they have chiral centers, and if so, how many and where they are. You can stop the video here and attempt to answer the question. The next practice question is, again, we have the same drug molecules from the previous slide, but now that you have identified the chiral centers, you need to assign the absolute stereochemistry of these, following the steps and rules I have shown you several slides back. And this is the end of this video. Thank you for listening.